Hi, it's Mr. Srikanth here, and in this video I'm going to show you how to do the questions in section 1A2 of your booklet, which is on surds and rationalising the denominator. So, you'll see at the top of the document there are some key points, and I've put those here for you. I'm hoping these are all familiar to you. So, what a surd is, which is the first one just up here, why you would use surds, and then two very important rules with surds, which is that with multiplication and division, if you multiply two numbers and then take the square root, that's the same as taking the square root of the first number, the square root of the second number, and multiplying the answers together, and the same is true with division, which means effectively that you can split the square root in a multiplication, and you can split the square root in a division. This is not true for adding and subtracting, and that's really important. So you can't say that the square root of A add the square root of B is the same as the square root of C. And one very obvious example of that is we know that the square root of 9 add the square root of 16 is 3 add 4. But if we did 9 add 16 first, which is 25, and did the square root of 25, that would be 5. 3 add 4 does not equal 5, so this is not true. And the same with subtraction. Okay, and then on to the next rule, which is that to rationalise the denominator means that you remove the surd from the denominator of a fraction. And there are two common types of rationalising that you'll both see in GCSE and you'll see more of in A-level, which is when you have a root on its own as the denominator. And the quickest strategy for dealing with that would be to multiply the numerator and the denominator by that same surd. The other possibility is that you have the sum or the difference in addition or subtraction, where one number is a surd and one number isn't. And then you need to multiply by what's called the conjugate. So you're changing the sign in front of the surd. A positive becomes a negative. If this had been a subtract originally, then this would become an add. But the first part, the non-surd part, remains the same. And that's linked a little bit to the difference of two squares, which I'm sure you'll have done in the expanding part on the first section of this document. Okay, we're going to look at the examples that are on the booklet. And I'm going to do some of these in two different methods. And you'll have been taught at least one of them, possibly both of them, when you were studying for your GCSEs. So, firstly, I'm going to do the prime factorisation method. So, the prime factorisation method means that we need to prime factorise 50 first. And there's a few ways you can do that. 50 is 10 multiplied by 5, which is 5 multiplied by 2 multiplied by 5. All of these are prime. And so what I'm being asked to simplify is 5 multiplied by 5 multiplied by 2. And you can see here that 5 times 5 times 2 is 50, so this is the same as the original question. But using the key point that we talked about a minute ago, which was about multiplication, we can say that this is the same as square root of 5 times the square root of 5 times the square root of 2. And then these two here that are the same, these are going to give me 5. And so I'm left with 5 times the square root of 2. So that's the prime factorisation method. The other method is to find the largest possible square factor. So with 50, I need to think of any factors I can, which are square numbers, and then out of all of the possible square numbers, I want to find the largest possible square factor. Now 50's got two square factors, 1 and 25. It has some other factors. We've got 5 and 10, 2 is a factor, etc., but those aren't square numbers. 1 and 25 are the only square factors, and 25 is the biggest square factor. So when we're being asked to simplify square root of 50, we're really being asked to simplify the square root of 25 times 2. And using the rule from the previous page about multiplication, I can split that up into the two separate parts. And then I can look at this and say, well, the square root of 25 is just 5. So I get 5 square root 2. And this is the largest square factor method. You can see that both methods rely on the rule that was on the previous page about multiplying and being able to split the square root across a multiplication. With this larger square factor method, you need to be a little bit careful. I'm just going to do another example, different to the one on the document. Let's say we were doing the square root of 72. Obviously, there are a whole bunch of different square factors here. We've got 1, 4, 9, and 36. These are all square factors. So let's just have a look at what happens if you choose the wrong square factor, if you don't choose the largest one. So we should use 36. That would be the best thing to use. But if we don't use 36, if we say root 72 is root 9 times 8, 9 times 8 is 72, and then say, well, this is root 9, root 8, which is 3 root 8. That's not wrong, but it's not complete. And the reason it's not complete is because root 8 can be simplified further. How can I simplify root 8? Well, I can carry on with this larger square factor method and say, okay, square root of 8 has some square factors, 1 and 4. So this is actually square root of 4 times 2, which is 3 root 4 root 2. And if I just go up here, 3 root 4 root 2 is 3 times 2 root 2, because the square root of 4 is 2. And 3 times 2 is 6, so that's 6 root 2. If I had chosen the largest square factor, which is 36, then this would have been much faster, because I would have got root 36 times 2, which is root 36 root 2, and the square root of 36 is 6, so that's 6 root 2. And if I'd done this with prime factorisation, then I would have done a tree. I'm not going to bother with the tree because I haven't really got space. I'll try and squeeze it in here. So 72 is the same as 2 times 2 times 2 times 3 times 3. You might want to just double check that. 2 times 2 is 4, 4 times 2 is 8, 8 times 3 is 24, 24 multiplied by 3 is 72. So with the prime factorisation method, I'd have been saying that the square root of 72 is the square root of... Now, I'm going to look at this and look for pairs, because square roots are useful if you can find a pair to go with it, because you know that when you multiply it by itself, you'll be back to the original number, because effectively then you're squaring a square root, which are inverse operations. So I've got a pair of 2's that I can match up there. So that's going to be root 2, root 2. Then I've got a pair of 3's that I can match up here. So that's root 3, root 3, and that leaves me with this at the end. So that's going to be just a square root of 2 on its own. And then using the rule from the last page, I can split this up. So that's square root of 2, square root of 2, square root of 3, square root of 3, square root of 2. These are going to give me 2. These are going to give me 3. And then I've still got square root of 2. 2 times 3 is 6, so this is 6 root 2. So those are the two methods. I've done it with two different values here, 50 like they've done in the document and 72. I wouldn't be surprised if 72 is on your list of practice questions, so that should be a nice easy one for you. I've done it all for you. Okay, now we're on to simplifying additions or subtractions with roots. Now again, I can use the prime factorisation method or the larger square factor method, so I'll do them both. The prime factorisation method looks like this, 147. You might know the divisibility rules, which say that if you add the digits up, 1 add 4 is 5, 5 add 7 is 12, and then if I add the digits of 12 up, that's 1 add 2, 1 add 2 is 3, and you might know there's a rule that says that if the digits end up adding to a 3, 6 or 9, then it's in the 3 times tables, so I know that 3 is a factor. Another thing I could do is look at this and say 147 is fairly obviously in the 7 times tables, because 7 goes into 14 and 7 goes into 7. So those are two different ways that I could start this decomposition. I will choose the second way. I'm just going to pause the video while I rub out the first method. Okay, so I'll carry on with this. 147 has a factor of 7, and I'm hoping it's fairly obvious that you multiply 7 by 21. 7's a prime number, so I'll circle that, and then 21 can be decomposed into 3 times 7. So I can write root 147, the first part, as root 7 times 7 times 3. I'm putting my pair at the start because I know that they're going to simplify to 7 later on. And then I've got 2 root 12, so that's going to be 2 times the square root of something, and again I need to do the prime factorisation of 12. Lots of different ways to decompose 12. I'll go for 3 times 4. 3 is a prime number, and 4 is 2 multiplied by 2. Those are both prime numbers. So that's going to give me root 2 times 2 times 3. And so this gives me root 7, root 3. Take away 2, root 2, root 2, root 3. These two together give me 7, and these two together give me 2, and 2 times 2 is 4, and 7 root 3 take away 4 root 3, 7 lots of something take away 4 lots of the same thing is 3 root 3, 3 lots of the same thing. So 3 root 3. Okay, and then the other method is the larger square factor method. So I'll start with the 12 because the 12 is fairly straightforward. 12 has a square factor of 4. 4 is the biggest square factor, so I can change root 12 into 2 root 4 root 3. 147, well, I need to notice really that this is 7 multiplied by something, and when I do that in my head quickly I realise that it's 7 times 21, so 7's a factor of 21, which means that I'm going to get 49 as a square factor. Another way you might notice that is to say this is quite close to 150, and 50 times 3 is 150, 49 times 3 is 147, so you might notice the 49 in a few different ways. So 49 is the biggest square factor of 147, so the first part is root 49 root 3, and root 49 is 7, root 4 is 2, and then again we're at the same as this line here on the first method, so now the rest of it's going to be exactly the same. So I can say that 2 multiplied by 2 root 3 is 4 root 3. And then 7 lots of something take away 4 lots of the same thing is 3 lots of it, so 3 root 3. Okay, now we're on to expanding brackets that have surds in them. And to be honest, this is exactly the same as when you're expanding brackets like you did in the first exercise. on this document, so this should be no problem to you. You know that when we're expanding brackets at Caledon, we use the grid method. So for this question, I'm just going to set it out like this: 7 add root 2 multiplied by 7 subtract root 2. This is quite an important type of pairing. This is a conjugate pair, and what it means is that we're going to end up with the peanut part probably ending up simplifying to 0. We'll have a look in a moment. So we've got 7 times 7, that's nice and straightforward. We've got 49. When we look at this box here, we've got root 2 multiplied by root 2. I'm going to ignore the signs for a moment. We've got the square root of 2 multiplied by the square root of 2. And the square root of 2 multiplied by itself is the same as square root of 2 squared. And that means the squared and the square roots are going to undo each other because they're inverse operations, which means I'm left with 2. But then I need to think about the signs. We've got positive multiplied by negative. So that will give me a negative 2. Okay, and then in the remaining two boxes, I've got square root of 2 multiplied by 7 and square root of 2 multiplied by 7. So both of those are going to give me 7 root 2. However, they are very slightly different. This one is a positive multiplied by a positive, so that is just positive. Whereas the second one is a positive multiplied by a negative, and positive times negative is negative. And then I'm sure you're used to doing the peanut for simplifying the cross terms. And you can see there that you've got 7 root 2 subtract 7 root 2. So this would be 49, add 7 root 2, subtract 7 root 2, subtract 2. The peanut section here is going to be 0, so that leaves us with 49 subtract 2, and 49 subtract 2 is 47. Okay, on to example 4. This is rationalising the denominator. So here we need to rationalise the denominator of 1 over root 3. And that's quite straightforward. It was a key point from the first page. And you'll remember that they suggested that you multiply by the square root of 3 divided by the square root of 3. Now, it's important to realise that what you're doing here is multiplying by 1. Something divided by itself is 1. So you're not changing this fraction, you're multiplying it by 1. When you multiply anything by 1, it doesn't change. You're just changing the way that it's written. And to multiply fractions, the most straightforward way would be to multiply the numerators together. That's 1 root 3. 1 root 3 is the same as root 3. And multiply the denominators together. That's root 3 times root 3. Root 3 times root 3 is root 3 multiplied by itself. So root 3 squared. Squaring is the inverse operation for square root. So that's going to undo the square root and we're going to be left with 3. Okay. There are some alternative ways if you've got a more complicated denominator. For example, if it was 1 divided by root 8. You could do 1 divided by root 8 by multiplying by root 8 over root 8, which will give you root 8 divided by 8. This wouldn't be as simple as it could possibly be, and the reason for that is because you can express root 8 in simplest surd form. And so if you think back to what we did a few pages ago, if I was expressing root 8 in simplest surd form, I might then say that this is root 4 root 2 divided by 8, and root 4 is 2, so that's 2 root 2 divided by 8. And then I can say, right, I know that I can simplify this fraction because 2 is a factor of the numerator and the denominator. How many 2's make 2 root 2? Just 1. 1 root 2 is the same as root 2. And how many 2's make 8? That's 4. So I get root 2 over 4. Or another way of doing this would be to do the simplifying first. And I could say this is 1 over root 8, which is actually 1 over root 4 root 2, which is 1 over 2 root 2. And so the only thing that I need to worry about here is the root 2 part. So when I'm multiplying now, by 1, my 1 could be root 8 over root 8, but I could also use root 2 over root 2. And that's going to give me 1 root 2 on the top, which is just root 2, and 2 root 2 on the bottom, which you can see root 2 times root 2 is 2, and 2 times 2 is 4, so that's going to give me root 2 over 4. Now, again, you might have 1 over root 8 as one of your questions in the practice exercise. I'm showing you these two different methods here because you might prefer one to the other. I would say that this top method is the most commonly seen method. The only thing about this method is that if you'd had a bigger number here, you're having to do bigger multiplications and then simplify, whereas this method allows you to simplify first and do smaller multiplications. You can see here that we multiply by root 2 over root 2, which is smaller numbers than root 8 over root 8. So you might want to consider that as part of your method. Okay, and so here's an example where that same scenario comes into play. I could simplify this in the most common method, which is to do root 2 over root 12. We're rationalising the denominator, so we don't need to care about the root 2 as the numerator. We care about the denominator of root 12. So we can multiply by root 12 over root 12, which is root 2 root 12 over 12. Know that 4's a large square factor, so I can make it root 2, root 4, root 3, all over 12. I'm going to reorder that numerator, and I'm going to put the root 4 at the beginning because I know that root 4 is nice and easy. That's just 2. And then I've got root 2, root 3. Root 2, root 3 is using that rule from earlier, the same as root of 2 times 3. So that's 2 root 6 over 12. And then I can say that 2 is a factor of both the numerator and the denominator. How many 2's make 2 root 6? Just 1 root 6. And how many 2's make 12? That's just 6. So I get root 6 over 6. Now, I can do the same question by simplifying first. So I can look at root 2 over root 12 and say at the start that this is actually root 2 over root 4 root 3. And I'm picking root 4 because root 4 is a square number being square rooted. And so I know that the square root of 4 will give me a nice straightforward number, 2. And then if I'm rationalising the denominator, the only part of the denominator which is causing me a problem right now is the root 3 part. The 2 is fine, so I don't need to worry about this. I do need to worry about the square root of 3. And to deal with that, I can multiply by root 3 over root 3. Remember here I'm multiplying by 1, same as I multiplied by 1 on the first method. My 1 looked like root 12 over root 12 earlier, now it looks like root 3 over root 3. So I get root 2 root 3 for my numerator and 2 root 3 as my denominator. For my numerator, that's the same as root 2 times 3. For my denominator, I've got 2 multiplied by root 3 times root 3. So root 3 is being squared, inverse operations, that's just 3. Okay, and the numerator is the square root of 2 multiplied by 3. 2 multiplied by 3 is 6. Can't simplify that, so that's just square root of 6. And the denominator, 2 multiplied by 3, that is 6 as well. So I get the same answer as before. Again here you can see that I simplified first, which kept my numbers smaller. The first method here is much more common. The second method uses smaller numbers, so you have to pick and choose which method you prefer. Okay, and the last example, this is where you have a denominator that has both a surd part and a non-surd being added together. And this time you have to be really careful to select what you're going to multiply by. A most common mistake is to multiply by 2 add root 5. And if we're multiplying by 1, which we have to do, otherwise we're going to change it, this would be 2 add root 5 as our numerator. Now, This isn't going to work, and I'm going to just show you why. It's not often that I would do the wrong thing and work through it, but I think in this case it's probably worthwhile. So I've got 2 add root 5 being multiplied by 2 add root 5 for my 2 denominators. I'm not going to worry about the numerators. I could put these in brackets just to be clear that I'm multiplying that entire thing by that entire thing, which is 2 add root 5 multiplied by itself. And you can see here that I'm going to get 4. In the last box of the grid, I'm going to get root 5 multiplied by root 5, so that's inverse operations. So that's going to be positive 5. But then in the other 2 boxes, I have the same calculation, which is going to give me 2 root 5 in both of them. 2 multiplied by root 5 and 2 multiplied by root 5, and both of them are positive times positive. So when I deal with these 2 bits in the peanut, I'm going to get a denominator of 4 add 4 root 5 add 5. And I can simplify these parts. But I don't want a denominator of 9 add 4 root 5, because that is not going to be any more simple or rational than what I had to start with. So instead of that, I need a better strategy. So if you think back to example 3, you might remember that that was a conjugate pair, and a conjugate pair is what you need here. We need to multiply this by the same numbers in my denominator, but with a different operation. I need the inverse operation of adding, which is subtracting, and that is my conjugate pair. Obviously, I need to multiply by 1, and to make this 1, my numerator and denominator have to be the same. So to rationalise and simplify this, I need to multiply out using expansion, which I'm going to do in the grid, to add root 5 multiplied by 2 subtract root 5. And this time we get 4 in the first box. We've got square root of 5 multiplied by square root of 5, so that's inverse operations, that's 5. But it's a positive multiplied by a negative, so that's going to give me negative 5. And then in the remaining 2 boxes, I've got root 5 multiplied by 2 for this box here, and root 5 multiplied by 2 for this box here. I'm just ignoring the signs for the moment. So both of those are going to give me 2 root 5. In this one, I had a positive multiplied by a positive, so that will just give me a positive. But in the second one, I had a negative here, negative times positive, which will give me a negative. And you can hopefully see that the peanut is going to simplify to 0, so that's just going to give me a denominator now of 4 subtract 5, and 4 subtract 5 is negative 1. So my denominator, when I multiply these 2 fractions, is going to be negative 1. For my numerator, I need to multiply, also in a grid, I haven't left myself much room here, 3 by 2 subtract root 5. This one's a bit more straightforward. 3 multiplied by 2 is 6. 3 multiplied by root 5 is 3 root 5. And on the second one, I've got a positive multiplied by a negative, so that's going to give me a negative. So I'll get 6 subtract 3 root 5. Now, that's not as simple as it can be written. And the reason for that is because I've got a negative on my denominator and a subtraction on my numerator. So the easiest thing to do here is to multiply this further by negative 1 over negative 1. And I'll get negative brackets 6 take 3 root 5 over 1. Dividing by 1 doesn't change anything, so now I've just got the numerator to expand, which will give me negative 6 add 3 root 5. And I can write that slightly more neatly by making the positive part the beginning. And so I get 3 root 5 subtract 6. Okay, hopefully you can now have a go at the practice questions I'm hoping that some of the questions I've invented as I've gone along through this video don't appear in your practice questions, but if they do, see if you can do them without looking back at the video.